Before I solve the Fibonacci sequence, I want to talk about a couple of its qualitative properties and introduce something called the golden ratio. So when Kepler was looking at the Fibonacci sequence, he wrote as 5 is to 8, so is 8 to 13 practically, and as 8 to 13, so is 13 to 21, or some shit like that. And what he meant by that was that if you look at any given term in the Fibonacci sequence, and I have the Fibonacci sequence written out over here, and you compare that, you look at the ratio between that number and the one next to it, and so here I'm looking at one term divided by the previous term, you'll notice that they approach a limit. So if you look at 1 divided by 1, that's 1, 2 divided by 1 is 2, 3 divided by 2 is 1.5, and so on. And the number that they're approaching is approximately 1.618, and this is a number called the golden ratio. But I'm not expecting you to take my word for that, because what I'm going to do in this video is I'm going to define the golden ratio, and then I'm going to later show you why this particular sequence of ratios approaches the golden ratio. So there's a couple interesting things to note here about the Fibonacci sequence. First of all, if you look at these ratios here, you'll notice that with respect to this limit here, this one is undershooting it, this one's overshooting it, undershooting it, overshooting it, and they alternate like this, and they keep doing that forever. And so you have a sort of oscillation going on there, and so that's kind of mysterious. And then another thing to notice is that if you plot these, the n versus f of n, you'll see that it's just it's a pretty predictable looking thing. There's nothing chaotic about it, nothing interesting really. It looks like you could draw a smooth curve through it. So what does this mean, having the n plus 1th term divided by the nth term approaching a constant number? Well, if you had a recurrence relation, f of n plus 1 over f of n is equal to a constant for all n, not just as n approaches infinity, we know how to solve this one, and I think this is actually the one I solved in the second video. If you multiply both sides by fn, you'll see fn plus 1 is equal to k times fn, and I found that the solution to that, I'm pretty sure it was in the second video, that was just going to be an arbitrary constant, which represents the beginning of the sequence times k to the n. So what we have here is an exponential function. So the fact that as n approaches infinity, the ratio between these two terms approaches a constant implies that the further you look on the Fibonacci sequence, the more it looks like an exponential function. So as an exponential n behavior. So what is the golden ratio? If we take just a line segment and we split it up in a particular spot so that the larger section, the ratio between the larger section and the smaller section is equal to the ratio between the entire line segment and the larger section, we can call that ratio the golden ratio. So in other words, if I call this section A, this section B, I'm making this split here such that A over B is equal to the entire length A plus B over the larger section A. And this ratio here is called the golden ratio, and denoted by phi. And it's actually pretty easy to solve for what it is. It's just an algebra problem. If I take this part here, this is just 1 plus b over a, and this is equal to phi. Over here, b over a, this is just the reciprocal of this, so this is just 1 plus 1 over phi is equal to phi. Multiply both sides by phi and you get this. So it's a quadratic. It's easy to solve. I can just shift some terms around here, and then you can just apply the quadratic formula. And interestingly interestingly, you'll actually get two numbers, so negative b, that would just be 1 plus or minus square root of b squared minus 4ac, so that's just going to be 1 minus 4, so it's just going to be 5 all over 2a. And so from here on out, I'm going to, if we had a minus here, then it would be a negative number because root 5 is greater than 1. Clearly, the ratio I was talking about here when I set up this picture was a positive one. A divided by b is equal to a plus b divided by a. The one I'm talking about was positive, and so I'm going to call that the golden ratio. So from here on out, I'm just going to say phi is just equal to the positive one. And then I'm also going to talk about the golden ratio conjugate, and that's just going to be the negative one. These are both important numbers, and to facilitate the next video where I derive the closed form solution to the Fibonacci sequence, I just want to here look at a couple properties of the golden ratio and its conjugate. So the first one is if you take the golden ratio and you subtract the golden ratio conjugate, you're just going to get square root of 5. If you take the golden ratio, you multiply it by its conjugate, then in the denominator you're going to have 4, and in the top you're just going to, this is a difference of squares, you're just going to have 1 minus 5, so it's negative 4 over 4, and so this is just going to be negative 1. So these are the two important properties that I'm going to use and cite back in the next video. And the one other thing, I just want to take this second one and notice that if you divide here, if I just want to look at the golden ratio itself, this would just be negative 1 over its conjugate, and then the other one is that if you want to look at the conjugate by itself, this is just negative 1 over the golden ratio.